So there's one more functional group that fits into the reactivity series, and that's the nitriles. And what you might notice about nitriles is that they have three bonds to heteroatoms. So they behave much like the other compounds in the reactivity series that three bonds to heteroatoms, like the carboxylate, the amide, the ester, the carboxylic acid, the anhydride, and the acid chloride. So we want to talk about the reactivity of nitriles and also how to make nitriles. So let's first look at the reactivity under acidic and basic hydrolytic conditions. So let's first do acid hydrolysis. In acid hydrolysis, we have a nitrile that is going to undergo a reaction with a catalytic amount of acid in the presence of water. And what we get here is the carboxylic acid. All right, so how does this work? Well, the first thing that happens is we're going to protonate the nitrogen atom of the nitrile, and that's really going to activate the carbon for nucleophilic attack. And so what happens is that we have a really, really electrophilic carbon center, and it's going to be attacked by water. And so we get an intermediate that looks like this. This is a charged intermediate, and so we can get a deprotonation. Proton falls off to give us a neutral species. And this neutral species will undergo a tautomerization. Now the tautomerization that happens here is very similar to the one we had last semester. You're going to form a carbon-oxygen double bond instead of a carbon-nitrogen double bond. And so we have this species, which we probably know as an amide. It's a primary amide. But what happens here is that it keeps going further on to the carboxylic acid. So under strongly acidic conditions, we said that we can hydrolyze amides to carboxylic acids. And so we're going to protonate. That's going to give us a protonated amide. And then we get, again, nucleophilic attack by a molecule of water. That's going to give us a tetrahedral intermediate. This tetrahedral intermediate is going to become deprotonated. It's going to give us a neutral species. That neutral species is then going to pick up a proton, this time on the amine, so that the amine is going to become now the better leaving group. And so we're going to have a tetrahedral intermediate that looks like this. And then we get collapse of the tetrahedral intermediate with loss of ammonia as byproduct. That's going to give us the protonated carboxylic acid. And then, of course, we get ammonia can deprotonate the carboxylic acid to give us the free carboxylic acid. Okay, so now that we have conditions for acidic hydrolysis, we want to talk about conditions for basic hydrolysis. So basic hydrolysis of amine, of nitriles, occurs when you take a nitrile in the presence of, let's say, sodium hydroxide. And the intermediate we get this time is the primary amide. All right, so let's see how this differs from the acidic hydrolysis. Well, we know that when we have a strong base, we're going to get the nucleophile is going to be much stronger, a higher HOMO, and so we're going to get attack of the hydroxide onto the carbonyl carbon, this nitrile in this case. And so that's going to give us this intermediate here. Right, so now it has a negative charge on the nitrogen. We're still going to tautomerize. But when we tautomerize, we're going to get an intermediate that has a negative charge on an oxygen atom. So we got, actually it's not even a tautomerization yet, it's a resonance delocalization. And then this is going to give us the final product, in which we have what's known as an imidate. And so we can protonate off of water. Right, to give us this species. And then that species will end up tautomerizing to give us the product. Okay, and so unlike basic conditions, this amidate intermediate is now even less electrophilic than the amides due to the negative charge. Right? It will still react to give carboxylates or carboxylic acids upon deprotonation, but more forcing conditions are needed. And so what we would need to do is to take that amide and treat it with sodium hydroxide, but this time heat it up. And what you'll get there is the carboxylic acid. And so again, you have hydroxide, it can attack the carbonyl carbon. You get an intermediate that looks like this. You get collapse with loss of amide. And this reaction is slow because amide anion is not a very good very good leaving group. And so you get the carboxylic acid plus the amide anion, and the amide anion is going to simply do a deprotonation to give you the carboxylic acid, the carboxylate plus amine. But then in order to get the carboxylic acid, you have to have a proton workup so that you get the reprotonation event happening. All right, so these are hydrolytic conditions under acidic conditions or basic conditions. So I'll place basic hydrolysis up here at the top. What about the reaction of nitriles with other types of nucleophiles? Let's see if we could react a nitrile with, let's say, a hard nucleophile like an organolithium or a reagent. Okay, so let's take an actual reagent. Let's take benzonitrile. And let's react benzonitrile with one equivalent of methyl magnesium bromide. And let's work that up with aqueous ammonium chloride. Okay, the product of this reaction is going to be acetophenone. Okay, so now how does this work? Well, we know methyl magnesium bromide as being a very nucleophilic partner here, and so the methyl magnesium bromide can of course attack the carbonyl carbon, and we're going to get an intermediate, and this intermediate is going to have a new carbon-carbon bond to where the nitrile used to be, and so we basically have something that looks like this. And this is not very electrophilic. And so this is only going to react once, right? And so normally when we had carbonyls that have more than one heteroatom attached, we had the Grignard reagents and their organolithiums reacting multiple times. But it only happens once for the case of the nitriles. And so this thing is pretty stable until you work it up. And so when we work it up, we're going to have a proton. And so that ammonium chloride is going to protonate the amine. And so you're going to get an imine. And then we're going to protonate it again. Right? So, and we protonate it again under acidic conditions, we're going to get an iminium ion. And this iminium ion is reactive. And this iminium ion will react now with water and do a hydrolysis, very similarly to where we had in the case of amines and enamines. And so we're going to do a nucleophilic addition to that iminium ion. All right, and we're going to get an intermediate that looks like this. Right, that's going to lose a proton. But then you can reprotonate it to give you a better leaving group. And so you've got now your ammonium ion here. That ammonium ion can, of course, be a good leaving group. So the water, the oxygen nucleophiles can move down to form a double bond, and you generate a leaving group, which is ammonia. And then you get a protonated ketone, but then that proton falls off to give you the product, which is your acetophenone. And just be mindful here that organolithium reagents also react the same way. Okay, so you can take Grignard reagents and then react them once with nitriles. You can react organolithium reagents and react them once with nitriles, and then upon acidic workup, you will hydrolyze the iminium to the corresponding ketone. All right, how about things like LAH? You have more type of hard nucleophile, and that's a hydride equivalent. So let's see. Let's take the benzonitrile again, and this time we're going to react with LAH. Okay. All right, so LAH, THF, minus 78 degrees Celsius, and we're going to work this up with 15% sodium hydroxide, just like we normally do. Now the product of this reaction is actually the fully reduced product, the amine. All right, so why does this differ than the other hard nucleophiles like the Grignard reagents and the organolithiums? Well, let's draw it out. So we have the aluminum hydride. Aluminum hydride is going to deliver a hydride to the nitrile, and we're going to get an intermediate that looks like this. We have a new carbon-hydrogen bond, and then we've got our aluminum bound to that nitrogen. What happens here is that the aluminum hydride can actually deliver a second equivalent of hydride in an intramolecular sense to give you a fully reduced product, right? And so you're going to basically have a hydrogen here, and then your amine is going to still sort of look like this, where you have a lithium counter ion. And then upon workup with 15% sodium hydroxide, your amide will become protonated by the water and deliver the product amine. And so this is a really good way of making amines from nitriles, is to take lithium aluminum hydride and fully reduce them. Now, this doesn't work with sodium borohydride, right? So I'll just say here that sodium borohydride is not reactive enough with nitriles. Okay, so we've talked about the reactivity of nitriles. We might want to talk a little bit about how to make nitriles. All right, so synthesis of nitriles. You know of a couple of ways of making nitriles already. The first one that comes to mind is probably the SN2 reaction from last semester. And so we can, of course, take something like a bromide alkyl halide and react it with, let's say, sodium cyanide and DMSO. And we're just going to get a simple SN2 reaction to give us the nitrile. And early in the semester, we talked about the cyanohydrin formation. So that's another type of reaction in which you can make a nitrile. And so you can take, for example, a ketone. This time we're taking acetophenone. React this with, let's say, HCN. And what you'll get is the cyanohydrin formation via nucleophilic addition of cyanide to a protonated carbonyl. Right, so that's two reactions we know of. The third reaction, which we don't know of yet, is something that has very similar reactivity to things we've seen before, and that's the dehydrogenation dehydration of a primary amide. Okay, so let's take an amide, and it has to be a primary amide, right? So this one here, and let's treat this with tosyl chloride and pyridine. Now, in the presence of tosyl chloride and pyridine, what we can do is we can dehydrate it, which means we're removing water. And when we remove water, H2O, from this system, what we're going to get is the nitrile. All right, so how does this work? Well, we're going to first react this thing with tosyl chloride. And so we can take the electrons from the nitrogen. Those are going to move down, form a double bond. The oxygen-carbon double bond is going to attack the sulfur and kick out chloride as a sort of an SN2-like reaction. And so what we get there is the following product. I'm going to abbreviate TS for tosyl. Okay, and I'm going to have positively charged nitrogen atom. Now this, of course, can be deprotonated by pyridine. And so pyridine can come along, do a deprotonation to give us a neutral species. And what happens next is that pyridine can come in again and do another deprotonation, but this time the deprotonation occurs with like E2 reactivity. And so we're going to deprotonate, form a pi bond, and lose the leaving group all at the same time. Right? And so, and this is a case where you're gaining another pi bond, so you're gaining a third bond there, and so you have your nitrile as your product. Right, so what I'd like to do is to size the reactivity series one last time, because we've come across a lot of different functional groups that can be placed within this reactivity series. And so I'm going to draw it slightly larger than normal, and I'll need two lines for this. And so we've got the least reactive, right? The least electrophilic partner, which is the carboxylate, all the way to the left of the reactivity series. And then we have the amide. And then the nitrile comes in. Right, and then we got the ester, which is about the same as the carboxylic acid. All right, and that's about a little bit less reactive than the ketone, which is less reactive than the aldehyde. And then we have the acid anhydride. And then we have the acid chloride. Okay, so far so good. We've got all of these species which are isoluble species. And then we draw a dotted line and we have the ones that are not isoluble. And I'm going to add a couple more here. So what I'm going to add next is the iminium ion. Okay, so this iminium ion here is really active. Iminium ion is also less reactive than the carbonyl, protonated carbonyl. And what we also said was that we have another type of molecule which is not isoluble, and that's the one which has the superleaving group on it. And this one is the last one. All right, so these here are not isoluble. All right. But they have this sort of special reactivity, and they're often intermediates in organic reactions that we've come across. All right, so we want to know the type of reactivity that we have for these molecules and where they are relative to one another. All right, so the acid chloride is the of the ones that are isoluble, the most reactive and the most electrophilic. Okay, and of course we have the ones that are not isoluble, which are all really electrophilic.